All right, can everyone hear me out there? Enter something into the chat. Okay, great, great. So I'm seeing some yeses. I like all of that enthusiasm. We are starting the talk off on the right foot. So welcome to the session. So today and tomorrow, we're going to talk about a variety of software level attacks that can be launched on both architectural and microarchitectural state. And so thank you everyone for attending the session. I know that things are very crazy all over the world. And so hopefully today and the next day, we're gonna make things slightly less crazy by sharing knowledge of how attackers can do foul things to our hardware and how we can defend against those attacks. And so here's a basic outline for what we're gonna talk about today and tomorrow. So today we're going to go through sort of an introduction to control flow integrity. So first I'm going to refresh everybody's memories about how virtual address spaces work, what's inside of them, how that content gets managed by the OS. Then we're going to talk about some basic attacks against control flow integrity. So we're going to look at buffer overflows, return to libc attacks, and a couple other different sort of garden variety exploits. We're also going to look at several defenses against those attacks. In particular, NX bits, no execute bits, Intel's shadow stack technology, and then address space layout randomization. And then on day two, we're going to get into some more advanced attacks and defenses. So we're going to look at memory vulnerability attacks. These things are often launched via a particular type of exploit called type confusion. These memory vulnerabilities then enable some more tricky to defend against attacks like return-oriented programming, often abbreviated as ROP, and then jump-oriented programming, oftentimes abbreviated as JOP or JOP. We'll then look at some more advanced defenses for these types of attacks. We'll look at how compilers can inject new instrumentation into code to protect against these control flow hijacks. So we'll look at compiler enforced CFI. We'll also look at Intel's technology for indirect branch tracing. This is a technology that allows a processor to try to track how control flow is jumping between various instructions in a program. And we'll also look at K-Bouncer, which is sort of a software level solution, which also leverages some hardware level tracing capabilities to try to introspect on program behavior. And then in the second half of day two, we will look at the beast that is known as SGX. So SGX is a series of technologies that are designed to allow secure enclave computation. It allows someone to run a program inside of a piece of memory that not even the OS or the hypervisor can touch. So we'll look at the design for SGX, and then we'll look at some vulnerabilities involving side channels that people have found for SGX technology. And I should note that today I'll teach for an hour, and then there's going to be a 30-minute break, and then I'll come back and then finish the rest of the class. Tomorrow on day two, there will be no break, so I'll just teach all the way through. And if you have questions during the talk, then please type those questions into the little Q&A feature that Zoom has. And then every 5 or 10 minutes, I'll take a look at the Q&A portion of the screen and then address those questions. All right, so let's get started. So here's the view from 30,000 feet of the problem that we're going to be talking about today and tomorrow. That basic problem is that when you look at C, C++, assembly code, these things are not memory safe. For example, there are no bounds on, there are no checks on bounds when you look at arrays. So for example, you can access an array out of bounds, and C or C++ or sort of raw assembly will let you do that. There's actually, there's also no validity checks on pointer arithmetic or dereferencing. If you want to dereference a null pointer, go live your life. That's basically C and C++'s approach. If you want to perform an inappropriate cast from some non-pointer type to a pointer type, these languages allow you to do that kind of thing. And as it turns out, not being memory safe, this is sort of a feature that enables a large variety of attacks. And a key insight is that modern operating systems do provide process-based address space isolation. What does that mean? That means that two processes cannot directly poke at each other's memory. And so this, of course, is good, right? Many of the processes on your machine might be distrusting. So it's a nice thing that they can't directly tamper with each other's memory state. The problem, though, is that process-based address space isolation does not isolate code from itself. So in other words, malicious inputs to vulnerable code may trigger inappropriate memory accesses. Inappropriate memory accesses that address space isolation won't prevent, because these inappropriate memory accesses, they just involve memory that's inside the current virtual address space. So if the attacker can feed these malicious inputs to a vulnerable program and trick that program into making inappropriate memory accesses, then a variety of bad things can happen. Attackers can use these inappropriate memory accesses to steal sensitive data from a process, or maybe even the kernel itself, subvert the process's control flow. In other words, force the program to execute code of the attacker's choosing, either code that the attacker has injected into the address space, or code that exists normally in the address space, but is being stitched together in ways that the original developer did not intend. Attackers can also use inappropriate memory accesses to escalate privilege. So that's actually a very important aspect of an exploit. So once the attacker takes over a process that's running with the privileges of some non-root user, the attacker can do anything that that particular user has the ability to do. But some types of memory exploits allow the attacker to escalate privilege so that the subverted process now runs as root or some other more privileged user. And then, of course, once that happens, then the attacker can do anything that this more powerful user could do. So this is the view from 30,000 feet. This is sort of the motive for everything that we're going to talk about today and tomorrow. Without memory safety, a bunch of attacks are enabled, which allow data theft, data tampering, privilege escalations, and all kinds of bad things. So before we get too much into the details of how these attacks work, let me just give you a very quick overview of what's inside a virtual address space. So over here on the left, what we see is a 32-bit address space, like you might see on a 32-bit x86 chip. And so what you have is at the bottom of this address space, you have the user mode state. Okay, so the user mode state, that's accessible to both user level code and to kernel privilege code. And at the top, you have the stack. The stack grows down, and we'll look at the stack in more detail in a couple slides. But the stack is where the program remembers the functions that it's made, the function calls that it's made. And so the stack is going to be used to store return addresses for functions. And it's also going to be used to store the local variables for each function. And then at the bottom of this user mode component of the address space, we see the code for the currently executing process. We see the static data for that process, as well as the heap. So the heap is the area of virtual address space where malloc data lives, or mmapped data lives. So that's sort of a dynamically growing region of memory for memory objects whose identity cannot be known statically. Then if we look up here at the top of the virtual address space, we see something that is very similar to what we saw at the bottom. So the top of the virtual address space is used for the kernel. These memory pages can only be accessed by the kernel, and they can only be accessed when the CPU is running in privileged mode. And so what we see is we have the kernel code and static data, and then we have the kernel heap and the kernel stacks. And so there might be more than one kernel stack, because the kernel might have its own kernel threads that are running, not on behalf of any user process, but just on behalf of the kernel itself. Also, the way that most kernels implement things like system calls is that when a user mode process makes a system call, the kernel has established a kernel level stack for that process. And so when the kernel is executing on behalf of a particular process, for example, to implement a system call, the kernel is using the kernel level stack that is associated with that process. However, that kernel level stack cannot be accessed by user level code. So if we look off to the right, what we see is a 64-bit address space, like you might see on a 64-bit x86 chip. And the basic contents are the same. Most of the current Intel chips now, they actually don't allow all of the virtual addresses to be valid. So you have this empty gap here, sort of in the middle, where there's this region of virtual addresses that are not valid. Nevertheless, you have basically the same setup as we see on the left. So at the bottom, we have this user mode state here, the stack, the heap, static data, the code. We have the empty gap, but then up here at the top again, we have the kernel level state. Okay, so now let's take a brief refresher of how calling conventions work. So calling conventions are essentially the contract that a callee and a caller adhere to make sure that function arguments get passed correctly during function invocation, and also to make sure that return values get returned properly once a function completes its execution. So on a 64-bit x86 system, the simplest case is that all of the arguments and the return values are integers or pointers. So in this case, the caller is going to store the first 6 arguments in the registers that I list up there: RDI, RSI, RDX, RCX, R8, and R9. And any remaining arguments are passed via the stack. And the callee, when the callee is finished, the callee is going to place a return value in RAX. So this is the System 5 calling convention. So just to make this concrete, let's say that we have this completely ridiculous function here. It's called foo, because of course. And so foo is going to take in a bunch of integer arguments, A through H, and then it's going to declare 2 local variables, local 0, local 1. It's going to set those local variables, and then it's going to return some integer value. So according to the System 5 calling convention, the first 6 arguments to this function are going to be passed through the registers that I just mentioned, RDI through R9. Now, if we look at the stack here, we'll see what happens with the other arguments and local variables that I mentioned. So if we look here sort of at the top of the diagram, this is where we see the G and H arguments. So the G and H arguments, remember, they sort of go over the limit of 6 arguments that are passed via registers. So they'll go up on the stack. We then see the return address here. Next, we see a saved RBP value. So the BP stands for break pointer. So you can think of the break pointer as being a convenient sort of pointer that allows the compiler to figure out where various information, various stack frames live. So we see that beneath the break pointer, that's where we see the space stored on the stack for the 2 local variables. And we will look in more depth and more detail at how these various registers like RBP and RSP get manipulated as the lesson continues. And so I see a question here: does each process has its own version of the kernel stack, kernel code, so on and so forth? So the answer is that the kernel code is basically, there's just one copy of that kernel code that lives in the high part of the virtual address space. So that high part of the virtual address space, it's actually mapped into every virtual address space, modulo some defenses against Meltdown and Spectre, which we might talk about tomorrow. So think of it as every user mode process has its own address space. However, the top part of every address space is the same. So it's got all this kernel state mapped in there. The bottom part, the user mode part of each address space, has unique per process state. And so hopefully that answers the question. All right. So this is how the calling convention works for a 64-bit x86 system. And so now let's look at how things work on a 32-bit x86 system. So in a 32-bit x86 system, the register pressure is high, and that's because there aren't a lot of registers, right? There's only, you know, the 64-bit version of the ISA has twice as many registers, but here for the 32-bit system, I think we only have 8 general purpose registers. So because register pressure is high, parameters are mostly passed via the stack, and they're going to be pushed by the caller in reversed order of the parameter list, and then the callee is going to place the callee is going to place the return value in EAX. So let's take a look at a simple example of how this might work. So now we've got a foo function again. Now it's got 4 integer arguments A through D. It's got 2 locals as before. So if we look at the stack, what are we going to see? We're going to see those arguments pushed onto the stack in reverse order of the parameter list. The return address will be here. So that's where foo should return to after it's done. And then once again, we have the saved break pointer, and then we have the saved local variables down there. Now, an important thing to note is that the stack actually grows downwards in memory. So this may be something that's like a little bit confusing if you've taken a data structures course and you're used to stack sort of growing up. But if you look at the actual memory layout in an address space, at least on x86, the stack is going to grow down. So for example, if we look sort of up here, this is where we would see the stack information for the caller, the thing that actually invoked foo. And then when foo gets called, it's going to push stuff on the stack. The stack is growing downwards like that. Okay, so let's see. So that's how the calling conventions work. That's how the address space is laid out. And so now let's go into a little bit more detail about how a function is actually called. So here we're going to see initial setup for the stack. We've got some information here for the caller function, its own saved break pointer. It's got a bunch of other stuff in its stack frame. RSP, stack pointer, points to the current top of the stack. So then imagine that a call instruction executes. So what that's going to do, that's going to push a return address onto the stack. And then it's going to change RIP, the instruction pointer. And so now we're inside code that belongs to the function that was just invoked. So now we're going to look at the function preamble. That is to say, the piece of code that's at the beginning of this new function that we've just called. So first, we're going to look at those first 2 instructions. So what are they going to do? So the first instruction is going to push RBP. So it's going to push the current version of the break pointer onto the stack. So it's a push, so we're going to move the stack pointer RSP as well. And so then the next thing that we're going to do is that we are going to update the location of the break pointer so that now the break pointer is going to point to the new break for this new stack frame that we're trying to construct. Now, next what we're going to do is we're going to make space for the local variables in this new function that we're trying to call. So remember, the stack grows downwards, so we're going to do a sub. We're going to subtract a value from the stack pointer. Stack pointer is now going to move down, and now we've got space for all the stuff that's in this new stack frame we need to create. And mostly that stuff is going to correspond to local variables that are in that new frame. And so there's a question, so what information is an RBP? So RBP is, just think of it just as a pointer, right? So just like RSP is a pointer, which is pointing to some memory location. In the case of RSP, it's the top of the stack. RBP is just pointing to some location in the stack, and that location happens to save the value of the old RBP, the old break pointer. So if we look at the current diagram that I'm showing right now on the screen, what we see is that the break pointer kind of helps the compiler to understand, like, okay, well, everything below the place pointed to by the break pointer, this is state that essentially belongs to the new function that's been invoked. And then the stuff that's below the break pointer, roughly speaking, belongs to prior functions that are sort of, their execution is paused because they're in the middle of invoking some other function. Okay, so that's what's in the function preamble. And so now let's look at the function epilogue. So what happens when a function wants to return? So first we're going to execute this, this leave instruction. And so this leave instruction, what's it going to do? Well, it's going to set the stack pointer to RBP and then pop that top of stack value into RBP. So we're going to move the stack pointer upwards. So now we sort of discarded all of that local function state that we push onto the stack. So for example, now all the local variables, they're no longer valid. Then we're going to reset RBP to its saved value, right? Because the saved value is what RSP is currently pointing to. And then we're going to move RSP because we were doing a pop, right? So we did a pop of that value, which is what set RBP to its new value. Then we move the stack pointer to that return address. Now, if we look back at the function epilogue off to the right-hand side, we see there's going to be a ret. So what is the ret going to do? Well, the ret is just going to pop the return value that's currently at the top of the stack into RIP. So RIP is the instruction pointer. So when you assign to RIP, you basically say, here's the next assembly instruction that should be executed. So the ret is going to pop the value currently pointed to by RSP into RIP, and then we are going to vector control flow back to the paused place in the function that called the one we're returning from. Okay, so that is an overview of virtual address spaces, how the stack works, how calling conventions work, and how we have the function epilogue and the preamble. Now let the Hunger Games begin. So we had to go through all of that sort of setup stuff so that we can understand how attackers can corrupt the activity of invoking code and then returning to the appropriate location. Okay, so now let's look at some buffer overflows. Buffer overflows are sort of like, you know, the granddaddy of all these various attacks that we'll discuss today and tomorrow. So before you can understand more advanced stuff like return-oriented programming, you've got to understand basic vanilla buffer overflows. So in this example, let's assume that we're dealing with a 64-bit x86 system. So let's say that we had the following function here. So it's called copy. It's going to take in a string as an argument. There's going to be a local variable, which is a character buffer. It's 16 characters wide. And then it's going to be used in a call to strcpy. So what does strcpy do? Well, like all good Linux programmers, we ask our friends, they say, look at the man page. Our friend is a jerk, but that's the way that things work in Linux culture. So you look in the strcpy man page, what does it say? It says the strcpy function copies the string pointed to by source, including the terminating null byte, to the buffer pointed to by dest. So the strings may not overlap, and the destination string dest must be large enough to receive the copy. Beware of buffer overruns, see bugs. So that's very interesting, right? So even the man page is telling us be careful of buffer overruns. So what exactly is this warning trying to tell us though? Okay, so imagine we had the following setup over here. This is the stack setup that we'd see as the caller is in the process of creating a stack frame for the copy function, the callee. So if we look at this, some code that we might see inside of copy at the beginning, we might see this sub instruction here. So this sub instruction is making space for the local variables in the copy function. So we have a buffer of size 16 bytes. So we know that we have to subtract at least 16 bytes from the stack pointer. On the particular compilation that I used for this program, it subtracted 24 bytes. most likely because of alignment reasons. So we do this subtraction here. We've made space for the buffer. Now we see these two move instructions. So what's going on here? Well, remember that on a 64-bit system, the calling conventions mandate that the first 6 arguments to any other function are passed via registers. So what we're doing right now is we're actually setting up the arguments for the call to strcpy. Okay, so that's what these move instructions are doing right here. So you can see that one of the arguments to the strcpy is just going to be the argument that was passed to copy itself, that str argument. The other argument to strcpy is going to be the stack pointer. So that's interesting, right? So I'm referring to this instruction right here. So why are we setting RDI to the stack pointer? Well, if we look at the diagram over here, the stack pointer is actually pointing to the buffer, the local variable in the stack frame for copy. So these two instructions are where we are setting up the arguments to strcpy. And then finally, we're going to call strcpy. And then this will push in a return address onto the stack and then jump to the first instruction in strcpy. Okay, so let's now suppose that str is attacker controlled. Okay, so what do I mean by attacker control? Maybe the string that's pointed to by str, maybe it came from a file that the attacker has written to or somehow otherwise has influenced the contents of. Maybe str is taken from the network. So maybe str came from a network packet, an HTTP request or response that the attacker generated. So suppose that the attacker gets to choose which bytes are in str. So what the attacker can do is that the attacker can leverage the fact that strcpy is going to continue writing bytes until finding a null character in str. Well, since the attacker controls str, the attacker can just provide a str that is longer than 16 bytes. That's longer than the destination buffer that is the local variable for copy. So what does this mean? This means that the bytes in str will overwrite the buffer, continue to overwrite stuff on the stack, and then eventually overwrite the return address on the stack. So if we look on the left-hand side, what we see is that if the attacker provides a string that's too long, then strcpy will start copying over the bytes in the buffer. Then we'll continue overwriting stuff on the stack. It'll overwrite the things, it'll overwrite the value of the saved breakpointer, and then it will overwrite the return address that copy is supposed to return to when it's finished. So that's interesting. So what are the ramifications of this? Well, what this means is that the attacker now chooses where copy returns to. Okay, so when copy finishes execution and invokes the ret instruction, the saved return address on the stack is now filled with values that the attacker selected. So what might the attacker want to do? Well, one thing the attacker might want to do is launch an attack called return to shellcode. So suppose that the attacker knows the address of buffer in memory. So in other words, the attacker knows this starting location on the stack for the buffer local variable. Let's also suppose that stack pages are writable and they're executable. This is currently no longer true on most systems, but let's just imagine this is true for now. So if both of these things are true, the attacker knows where the buffer lives, and the attacker knows that stack pages are both writable and executable, then what the attacker can do is use the buffer overflow to fill the buffer with x86 instructions, and then overwrite the return address on the stack with the address of buffer. So if we look back to the left, what this means is that all of this stuff here in the array, and maybe up here as well, it's filled with literally the bits for x86 instructions. And then this return address is going to point to the beginning of the buffer. So when the copy function tries to return, the instruction pointer is going to be set down here. The instruction pointer has been set to a location on the stack, but we're assuming for now that the stack is executable. So what's going to be at the instruction pointer, instructions that the attacker got to select. So what kind of shell code might you want to put in that overrun stack area? So here's an example of the shell code. Now what I'm going to show you is C code, okay? But what the attacker would do is that the attacker would sort of construct their shell code by writing a C program and then compile it, just like any of us would do using GCC or Clang or whatever, get the binary output, and then put that binary output in the malicious attacker controlled string. So what might be an example of shell code the attacker might use? So the attacker might want to create a socket, for example, connect that socket to an attacker controlled machine. Then the attacker might want to bind that socket file descriptor to the exploited program standard in out and error using the dupe2 call. So remember sock in this example, it's just a file descriptor. And so what these dupe2 calls allow the attacker to do is to say, well, I want to bind the standard in, standard out, and standard error of this program that I've injected shellcode into. I want the in, out, and error to be bound to the socket. So in other words, like whenever this program now tries to write to standard out, aha, that's going to be a write to the socket. Whenever the program tries to read from standard in, aha, that's going to be a read from the attacker controlled socket. And then for the final coup de grace, you can have the shellcode exec a shell. So this is actually why shellcode is called a shell, because one of the main goals of the attacker is to get a shell running with the privileges of the program that's been exploited. And so at this point, we do the exec, we start running a shell. The shell standard in, out, and error have been bound to the socket. And so now the attacker can write to the socket to send stuff to the shell, and the attacker can read from the socket to get the output from that shell that's running on the remote machine. So at this point, the attacker says, I'm at your base, I'm running my code. This is very bleak, of course, but luckily there are some defenses that we can use to prevent these types of attacks. There is, in fact, hope. But let me now just pause very briefly and see if there are any questions on what I've been talking about for the last 10 minutes or so. Just looking at the Q&A feature, give people maybe 10 more seconds to type if they have a question. This is the delightful experience of Zoom where everything becomes slightly more awkward. Okay, great. So I'm not seeing any questions in the Q&A. I'll check that again in about 5 minutes or so. So let's look at some defenses against this. Oh, I just saw a question come in. Oh, someone's saying the Sony PSP didn't have the no execute bit, and it was very easy to find buffer overflows. Yeah, so as it turns out, like some of the techniques that I'm going to discuss, they should be widespread, but they are not widespread in some sort of use cases, which makes a lot of these very classic attacks still very relevant. So for example, why is it still very relevant to look at vanilla buffer overflows? Because a lot of IoT devices, for example, are susceptible to this attack that I just described the last couple slides, right? For a lot of IoT devices, you don't have to engage in all of the black magic sort of insanity that I'll describe, particularly on day 2 of this lecture. You just do a vanilla buffer overflow. So it's very important to understand how this basic stuff works, because if you do decide to attack IoT devices, and I'm not telling you to do that. I'm just saying, whatever, you know, times are tough. You got to make some walk around cash. If you do decide to attack IoT devices, a lot of these very simple attacks will work right out of the box. Okay, so how might we defend against some of this stuff? Well, as the person kind of alluded to in the comment they just posted, one very important defense is this notion of write, exclusive, or execute. Okay, so in the old days, like in the setup I just described, or in the modern days on poorly configured machines or some IoT devices, for example, it used to be the case that if you had a page table access bit of writable, that implied executable by default. right? So in other words, if you mark your stack pages as writable, which they should be, because you need to be able to write your local variables, well, that also meant by default that your stack pages were executable. So if we want to stop the type of shellcode injection that I just showed you in the last couple slides, then what you can do is you can add a new type of page protection called basically a no execute bit. So the idea here is that if the CPU tries to jump to an address that resides on a no execute page, then the hardware generates an exception. Then the OS takes over and the OS can kill the program. So what you want to do is that you want to mark your stack and heap pages as no execute. Now I put here, there's sort of this caveat, right? Because there are some types of programs that legitimately need to generate new code on the fly. So perhaps the most sort of popular example of this is a web browser, right? So a web browser is going to download some JavaScript code, and to make executing that JavaScript code fast, the browser is going to want to dynamically JIT that code, just in time compile that code, and then emit some native machine instructions, x86 or ARM or RISC-V or whatever, on the fly, and then execute that code directly. So this actually can be exploited, this fact that some programs perform JITs. So the attacker can take advantage of this to try to, for example, construct specially crafted JavaScript code that will JIT to bytes that are good for the attacker in some way. And we'll discuss some of this stuff in more detail tomorrow. So anyway, so this defense of having no execute bits in page tables, it has some nice properties. So one property is that you don't have to modify applications very much, if at all, right? So you can modify, let's say, the operating system so that it by default marks stack pages and heap pages as no execute. But other than that, applications don't need much modification. User level applications don't need much modification. The other nice thing about this is that the protections that are provided by the no execute bit, they're actually implemented by hardware. So, it's the hardware, the memory mapping unit, that's sort of checking these protections to look and see if code is trying to jump to a non-executable page. So this is fast. And it's fast in contrast to a solution where, let's say, after every instruction, user mode code would trap to the OS. Then the OS would sort of look to see if the jump was valid. That would be a nightmare, right? Because context switches are very expensive. So this no execute bit thing, this has become very popular. It's standard on most of the popular chips you'll see now, x86, AMD, ARM chips. This is sort of a sort of basic thing that you want to do now if you design a chip. And so just to make this concrete, here we see what page tables look like on 64-bit x86. And so over here to the left, we see CR3. That's a special control register. You can think of this as being the page table pointer. So whenever the OS does a context switch to a new process, the OS is going to set this special CR3 register to point to the page table for the current address space. And so the page table is basically, it's like this tree-like structure. So CR3 points to this top-level page table structure. We then use some bits from the virtual address to translate to select a particular entry in this high-level page table. This is a page map level 4 in Intel parlance. That page table, a page map level 4 entry points to what Intel calls a page directory pointer. We then use some additional bits in the virtual address space to find an entry in here, so on and so forth, until we find a mapping which finally tells us here's the physical page that contains the physical address to which the virtual address is mapped. And so if we look at, for example, one of these PTE entries here, the last level page table entries, what do we see? Well, one of the things that we see in that PTE is the physical address of the physical page that contains the mapped virtual address that we're trying to translate. Off to the right, we'll also see some bits for things like, is this page writable? Is it user mode accessible, or is it only kernel mode accessible? Is it even present? Is it even mapped into memory right now? And then what we'll do with the no execute bit is we'll just add that over here to the end on that, to that bit 63 there. And so this is the bit in the page table mapping that the hardware is going to check to determine if a jump to a particular, if like a call to a particular address is going to be a valid one. Okay, so we did it, right? No more attacks, no execute bits, stop everything. This, of course, is a big fat lie. That's lol, that's the concatenation of two lols. That's how intense the lols are. So, of course, there are still attacks that can be launched. And so what security ends up being, as you probably already know, is a cat and mouse game, or in this case, a rock climber Godzilla game. So the attackers do something, people try to create defenses against that stuff, and then you just go back in this cycle again and again. So, oh, okay. So let's see, someone had a question. So what are bits 48 through 62 used for? Let me go back to the other slide here, 1 second. Yeah, so the question is, what are these bits over here for? So as it turns out, for a very long time on x86 machines, even if the machine was 64-bit, not all of the address bits were valid. So for a long time, only these bits 0 through 47 were valid, and then those remaining higher order bits were just sign extensions of that 47th bit. And so there's no, and so the reason for this is that having to create memory translation hardware for the full 64-bit address, it can definitely be done. It would just require more circuitry. And if people weren't, if applications weren't really needing to use those missing address bits, then why go to all the hassle of having to add hardware to handle this extra translation work? Now, new Intel chips do use more of the virtual address space. So I think it's something like maybe 56 bits now, like the very newest Intel chips. Don't quote me on that exact number, but newer Intel chips will use more of that high order sort of virtual address space. Okay, let's see here. So another question, so if 4 kilobytes is marked no executable, but the stack frame for the process might not require 4K, so will space be wasted? Yeah, so if I understand the question correctly, yes. I mean, there's a lot of aspects of sort of operating system management where you're forced to do things in a manner that is page aligned. Because a lot of the OS system calls, things like mmap, improtect, things like that, it's all done at a page granularity. So yes, it could be possible that, for example, you have a user mode process. It has functions that have very few local variables. The function doesn't have deep call chains. It doesn't, use a lot of recursion, things like that. In which case, yeah, there might be some waste there if, for example, the process also had a very large amount of code. So you might want to put some code like in part of that 4K page that's totally allocated to the stack. But long story short, yeah, there might be some waste. It ends up not being that big of a problem in general, though, because address spaces are so huge, and because typically just 4K of stack is not enough. Okay, so let us now move on to see how the attacker can still do bad stuff, even if there are NX bits, no execute bits in place. So we're looking at the same function that we looked at before. We're looking at this copy function. We're assuming, once again, that the stir argument is controlled by the attacker. So what does this mean? Well, we know that the attacker in this setup can still determine where a copy returns to, because NX bits don't actually stop the buffer overflow, right? So the attacker can still supply a too long string, and that string can still use strcpy to overflow part of the stack. But there is a challenge now. So even though the attacker gets to choose where a copy returns to, the no execute bits actually prevent injected shellcode. So in other words, if the attacker wanted to add a shellcode here and then overwrite this return address with the beginning of the buffer, well, that's where NX bits would cause the fault. The OS would get involved and the OS could kill the program. So what can the attacker do in this case? Well, never underestimate the sort of intelligence of the criminal mind. So there are ways to still launch control flow attacks here. One of the sort of first responses by attackers was this notion of a return to libc attack. So what's the idea here? Let's assume that the attacker knows the location of libc in the address space. So if we look over to the left in the diagram, let's assume that that's where libc lives. It's a dynamically mapped library. It's got a bunch of code in there that we all know and love. Among other things, it's got a function called exit, which you can call to have the program exit. It's a very accurately named function. So let's assume that the attacker knows the location of libc in the address space. Now you'll note that in several of these attacks, I've made the assumption that the attacker knows where various things live. As a preview of coming attractions, this is one type of defense that you could imagine trying to launch. You could try to randomize the location of things so that the attacker doesn't know where things are. But we'll talk about that in more detail in a bit. So let's for now assume that the attacker knows the location of libc in the address space. So what the attacker can do is overwrite the return address on the stack with the address of a libc function. So for example, like in this case, maybe we want to overwrite the return address to be the first instruction of the exit int status libc call. Now, what's interesting is that on a 32-bit x86 system, if you think back to the calling conventions, the arguments were passed on the stack. So depending on how clever the attacker is when they do this overwrite, what the attacker can do is actually continue the overwrite beyond the return address on the stack. In other words, continue to overwrite stuff up here and actually try to be clever and try to pass some arguments to the libc function on the stack. Now, for 64-bit x86 systems, this doesn't work because the buffer overflow can only overwrite memory values. It can't overwrite registers. But like in this example, the attacker can force the program to just exit arbitrarily. Now, the challenge, I mean, it's probably not a challenge from the attacker's perspective, is that since the attacker can't control that int status argument, because that int status argument lives in a register, which the attacker isn't able to overwrite with the buffer overflow, the program's going to exit with some arbitrary value, whatever happened to be in that register that would have held the first argument. But if all the attacker is trying to do is just force a program to exit inappropriately, then this attack just sort of works right out of the box. And so I see that there is a question about what about ROP chains? Yeah, we will talk about ROP chains, but that's going to be part of tomorrow's discussion topics. So yeah, we'll definitely get to that. Okay, so return to libc attacks are sort of a clever way to exploit the fact that as long as the attacker can control a return address, well, the attacker can basically make that return address point to pre-existing code in the address space. Not injected code, because no execute bits prevent injected code. But if the attacker is clever, the attacker can analyze the binary, for example, offline, and then try to figure out, oh, well, I can redirect control flow to this pre-existing bit of code that will do some mischievous action. So the types of buffer overflows that we've been talking about, they're all sort of like specific instances of attacks that are oftentimes known as code pointer corruptions. So a buffer overflow allows the attacker to overwrite code pointers in the path of the overflow. So a code pointer is just an address that corresponds to executable instructions. So for example, on the stack, return addresses are a form of code pointer. Function pointers are also a form of code pointer. So imagine that we had this the following function, which I have cleverly named copy2, because this is the second one. So what do we see here? So in this first line here, this is the horrid C syntax for a function pointer. So this is a pointer to a function which takes no arguments and which returns an int. So imagine that what copy2 does in this first line is that it sets this function pointer to point to foo. So foo is just some other function that was defined somewhere else in the code. Okay, so this is how function pointers work. So then, as before, we have this sort of exploitable piece of code here. We have the buffer, we have the vulnerable strcpy down here, and then we have an invocation of the function pointer. So once you've set the function pointer, you can invoke it just like any other function. So in normal situations, this invocation to the function pointer is going to invoke foo. Now the problem though is that this function pointer here is vulnerable, right? It's vulnerable because of the buffer overflow. So as the buffer overflow goes up, we actually see that the F pointer here is in harm's way. It can actually be stomped over by the buffer overflow. And so what does that mean? Well, that means that if the attacker can overwrite that function pointer, then down here at the very end of this copy2 function, this invocation of the function pointer, that's now controlled by the attacker. So now the attacker can make F pointer jump to some code location of the attacker's choosing. And so these types of attacks can also occur on the heap too. So you can imagine that there are function pointers on the heap. There are V pointers. V pointers can be both on the stack and on the heap. So we're gonna look at V pointers in more detail tomorrow when we look at type confusions. At a high level, V pointers are some mechanism that allow C++ to implement objects in like polymorphism and things like that. Roughly speaking, each object has a V pointer, and the V pointer points to a V table, which is a bunch of function pointers for that particular class to which the object belongs. And so by controlling V pointers, that allows the attacker to control how object-oriented method calls actually get bound to code. But like I said, we're going to look at that in more detail tomorrow. But for now, the high-level thing you should take home is that there's a bunch of different types of code pointers that can live both on the stack and on the heap. And so control flow vectors to a place of the attacker's choosing once one of these corrupted code pointers is used. So I've just said a bunch of stuff that says that the attacker wins. I don't know if Zoom is fully supporting the amazing frame rate that's necessary to see this dancing attacker, but you know, I'm looking at it on my screen. It's amazing. So it seems like there's all these vulnerable code pointers that the attacker can sort of exploit to divert control flow. So what can we do to make things better? Well, before I talk about that, let me ask one question. Why doesn't the operating system detect these buffer overflows, right? We're always sort of taught that the operating system is kind of like this paternalistic character. You know, the operating system is going to be sitting around trying to figure out, you know, if someone's trying to tamper with my state, and if so, it's going to punish people and so on and so forth. So a very common question is, why doesn't the operating system detect buffer overflows? So roughly speaking, the kernel only executes code in two situations. User level code is issued a system call. So for example, user level code wants to read from the disk, send a network packet, spawn a new process, so on and so forth. So when the user level code issues a system call, the kernel has to get involved. The kernel also gets involved when an external event occurs. So this is something like a timer interrupt firing, maybe a storage device has indicated, hey, that IO that you wanted me to complete, it is now complete. So, you know, what this essentially means is that the kernel is mostly passive, and it relies on page tables in the memory mapped unit, the thing that sort of does the translation from virtual to physical addresses by walking the page table. The kernel essentially relies on the page tables in the MMU to isolate processes from one another. but the kernel is not sort of actively inspecting every little thing that a process does. And so what this means is that, well, a lot of attacks can still occur, like these buffer overflow attacks, because page table-based isolation doesn't protect a process from itself. And so this is why the operating system can't sort of do something special when a buffer overflow occurs, because in general, the kernel is just sitting around waiting for something to happen. So what are solutions to this? Well, one solution is to just don't use computers, right? I think it's pretty obvious now that like computers may not be the best thing for us. Facebook's a good example of that. So we could just not use computers. But of course, I was not brought into the summer school to tell people not to use computers, even though that's what I really believe. So one defense mechanism that is very common now is called stack canaries. So how do stack canaries work? So the basic idea is you want to place a special value in memory between a stack frame's local variables and some memory location to protect. So for example, the return address for a frame. And then immediately before the function returns, we want to check whether the stack canary value has changed. And so basically we have something like this. So we have the buffer, the return address, the canary sort of sits in between. And so a buffer overflow that needs to get to the return address is going to trample the canary too. So as we see the buffer overflow going upwards in memory, we see the canary value being changed to some attacker controlled one. And so then what the system can do is basically notice at the moment that a function returns, hey, this red bird does not equal this yellow bird. So some type of bird-based crime has occurred. Time to call the authorities. So what does this look like sort of at the implementation level? So let's imagine, once again, that we're about to invoke a new function. So a call instruction is going to execute. That's going to push a return address onto the stack and bump down the stack pointer. Then in the function preamble, what do we see? Well, we have the standard stuff about saving the old break pointer on the stack, and then we're going to update the new position of the break pointer. Now we're going to make some space for local variables. This is similar to what we were seeing before. But now we're going to copy the known good canary value onto the stack. So that's what these sort of incantations are that are highlighted in yellow here. So this weird like FS0x28 stuff, this is basically using this weird segment register x86 nonsense. Roughly speaking, you can think of this as like a base plus offset calculation. So this is saying, given the base address in this FS register, I want to take the memory value that's at offset hex 28 from it and store it to REX. So this is the known good value of the stack canary, and then we're basically moving it onto the stack. So if we look off to the left, we see, that's where the canary is. Then we're going to zero out the known good value from REX because paranoia, don't want that canary value hanging around where the attacker could see it. And then in the function eblog, what do we see? So we basically move the canary value from the stack into REX, and then we XOR it with the known good value of the stack point, of the stack canary. And so because of the way that XOR works, if the value of the canary that was taken from the stack is equal to the known good value, then REX is going to be set to 0 by this XOR instruction here. And so then depending on, what the comparison ended up revealing, we're either going to jump to the code that does the function return if the canary was good. Otherwise, we're going to jump to some function stack check fail, which basically is going to, print out an error message or crash the program, something like that, because the canary was detected to be corrupted. Okay, so that defense was for stack pointers, stack canaries. And so we're also going to talk about 3 other defense mechanisms: shadow stacks as enabled by Intel CET, address space layout randomization, and randomizing struct layouts. So at this point, though, we're going to take the break. I see there's some questions there. Just keep them queued up, and then I will answer those questions when I come back from the break. So now we're going to start the 30-minute break. So we are now back to the discussion. The amazing second half of the lecture will now begin. And so now let me, before I get into some of the discussion of the other defenses, let me now get to some of the questions that people had asked right before we'd gone for the break. So one question from Daniel Bailey is, where does the initial canary value come from? And what stops the attacker from basically learning it and then including it in their overflow payload? So this is a great question. Let me try to go back a slide. Okay, so 1 second. Okay, so if we look here, okay, this is where the known good value is being copied from this place in memory onto a place in the stack. So if we look at this incantation here, like I mentioned, this is sort of like this weird x86 segmentation nonsense, but you can think of this as a base plus offset address. So you can think of FS as having, it's a pointer to some place in memory, and then this little thing here in parentheses, that is the offset. So yeah, so then the question is, why can't the attacker just figure out where that good value is? So that's true. If the attacker had what's known as a memory read vulnerability, which we'll go into more detail about that tomorrow, and if the attacker happened to know where in memory to look for the canary, then you're exactly right that the attacker could just include that canary value in the buffer overflow. Now, as it turns out though, the reason why we're using this sort of weirdo notation here to load the canary, so this is a register, right? So this means that even if you have a multi-threaded program, right, each one of those threads is going to have a different register set. And so this value of FS, which you can think of as the base for this base plus offset calculation, it can be randomized, right? So, every time the process loads, each thread gets, sort of a random value for FS. So what that means is that even if the attacker has a memory read vulnerability and could read, let's just say, all of memory. We're giving the attacker a very powerful skill set here. The attacker wouldn't know exactly where to look. Now, I will say that, like back in the olden days when canaries were first being deployed, people would sometimes make mistakes in the implementation that allowed the attacker to know the canary. So as a sort of trivial example, what if the canary were the same value across all instances of a program and across all instances of a particular OS? So then the attacker can just load a program on the attacker's local machine, use GDB to look at the stack, find the canary, and just put that in the buffer overflow packet. So, or payload, excuse me. So that's exactly right. That's a very good question. The attacker shouldn't be able to discover the canary value. Otherwise, they just put that in the buffer overflow payload. Yeah, okay, so I think there was another question along those lines too. And by the way, when we talk about ROP attacks tomorrow, ROP attacks possibly enable a venue for the attacker to learn what that canary value is. As we'll discuss in more detail tomorrow, what a ROP attack allows the attacker to do is maybe the attacker won't jump to the beginning of a function, as in a return to libc attack. Instead, what the attacker will do is maybe jump to an arbitrary place in the middle of some function. And what if that place that the attacker jumps to is an assembly instruction that, for example, loads the value of the canary into a register or loads it into memory, kind of like this instruction we're looking at right here. Well, if the attacker can stitch together a bunch of these gadgets, the attacker could try to use those stitched together pieces of code to then learn the canary. So we'll discuss some of that stuff in more detail tomorrow. And then there was a final question from Jens about stack canaries. So who checks the stack canary? Is it the hardware, the OS, or the application itself? So it is the application itself. So if we look at the slide, let's see. So all this stuff here in the function epilogue, that's all stuff that is in the code of the application itself. So this epilogue, if you disassemble a program that you yourself compile, you can see this code. This is user level code. So it's basically user level code that right before the function returns is going to pull the value of the canary off the stack, compare it to the known good value, and then depending on how that check resolves, we're either going to return from the function as normal or call this sort of failure function here. That's user mode code too. Typically what this will do is it might print out an error message, then it'll crash the program or exit the program. Alrighty, so that's how stack canaries work. And so in the remainder of today's discussion, we're going to look at some additional defense mechanisms besides stack canaries. First, we're going to look at shadow stacks, which is a hardware-based mechanism which Intel has introduced. Then we'll talk about address space layout randomization. And then finally, we'll quickly talk about using the compiler to randomize struct layouts. Okay, so first let's focus on Intel's CET. So CET refers to Intel's control flow enforcement technology. So CET is going to ship with the Tiger Lake chips that are coming out this year, and also upcoming Xeon chips are also going to support CET. So one thing that CET provides is this notion of a shadow stack. So it's a separate hardware managed stack that's going to track call and read information. So the basic idea is pretty simple. During a call, the hardware itself, not the OS, not the application code, the hardware itself is going to push the address of the instruction after the call onto the shadow stack. So the instruction after the call, that's where the function that's being invoked by the call should return to. So during a call, we're going to push the address of the correct return target onto the shadow stack. And then during a return instruction, the hardware, not the OS, not the user level code, but the hardware is going to pop the addresses from the shadow stack and the regular stack and then see whether or not they match. So imagine that we have this simple code here. So we see this function foo, and foo is then going to call bar. And so before foo actually invokes bar, we can imagine that both the normal stack and the shadow stack are empty. The normal stack is what we were just looking at in the prior slides in the class today. The shadow stack is this new hardware managed thing that I just introduced on this slide. So imagine that foo makes that call to bar. So what's going to happen? So on the normal stack, we're going to push the return address onto the normal stack, and that return address is saying, hey, you should return back to foo. That's what that little arrow notation means. Meanwhile, when the call instruction executes, the hardware is going to automatically push the address of that legitimate return target onto the shadow stack. Okay, so the hardware does that automatically. Basically, the implementation of the call instruction is going to automatically place that correct return address onto the shadow stack. So now let's say that we're inside bar right now. Bar calculates y times y, then it returns. So what'll happen is that that's gonna, the C level return statement boils down to a x86 level ret instruction. And so then the hardware is going to pop an entry off the normal stack. It's also going to pop an entry off of the shadow stack. Then it's going to compare them and say, are these two things equal? In this case, they are equal. So this means that CET will declare that there has been no corruption of the return address on the stack. All right, so now let's change things up a little bit. So now we have a function foo that is going to call some ominously named function vuln. So that name should not fill us with confidence. And so what's going to happen here? So foo makes the bad decision to call a function called vuln. That is going to result in a return address being pushed on the normal stack, as we've seen before. Also, the hardware, upon seeing the call instruction, automatically pushes the return address onto the shadow stack. Now we come into vuln. Ah, man, It's our ancestral enemy, the strcpy function. When will you kids learn? Stop using this function. This causes a buffer overflow. And so what that's going to do is now if we look at the normal stack, so now the return address on that normal stack has been replaced by some evil value, some value that's sort of been chosen by the attacker. So eventually the vuln function will return. That's going to boil down to an x86 level ret instruction. So now CET is going to look at the entries on the two stacks. It'll pop from the normal stack, pop from the shadow stack, compare those two values, and now CET is going to say, oh my goodness, these two return addresses are not equal. So what will happen is that now the CPU is going to raise a special CET fault, a control protection exception. So that exception is going to cause the program to trap to the operating system, and then the operating system can kill the program. Okay, so let's see. So I see a couple questions here. Let's see here. So one question is, how is this hardware push to pop from the shadow stack initiated? So it's initiated by the CPU itself. So there doesn't have to be any new code in the user level code. Basically what will happen is that, like, if you were to disassemble the program, you know, let's say we look at foo. So that call to vuln, that's going to result in an x86 level call instruction. And so literally the circuits or the microcode that implements the call instruction is going to push something onto the shadow stack. So the programmer doesn't have to worry about that. Now there is some shadow stack management stuff, which I'll discuss in a second, that the programmer or the OS does have to worry about. But just the pushing and the popping of stuff from the stack, in the common case, developers don't have to worry about that. Let's see here. So one question from Stefano. So did Intel release information about the shadow stack size and how it works? Yes. So we'll talk about this in a couple minutes. Actually, it's on the next slide. So yeah, let me actually go to the next slide, which might answer some of these questions. Then I'll return to the questions. Okay, so where does a shadow stack live? Very popular question. So in Intel's implementation of CET, it actually lives in virtual memory. You don't have to implement a shadow stack like this. You could imagine an implementation where the shadow stack actually lives in some special hardware buffer, let's say, that isn't part of the virtual memory space, and that is only used for shadow stack stuff. But that is not the way that Intel chose to implement it. So in their implementation, the shadow stack lives in virtual memory, just like the regular stack, the heap, the code, all that kind of stuff. But so of course the question is like, well, but if it lives in virtual memory, can't it be tampered with by the attacker? So as it turns out, CET protects the shadow stack using page table protections. So by setting the page table protections correctly on the shadow stack, this means that the only sort of instructions that can modify the shadow stack, for example, push and pop stuff, are calls and rets, which is what I just discussed. So, you know, when a call takes place, the circuits or the microcode that implements the call will push something on the shadow stack. Same thing with the rets. When a ret is executed, the hardware or the microcode that implements it will pop stuff from the regular stack and the shadow stack. But there are also some shadow stack sort of management instructions that have to be able to manipulate the shadow stack. So an example of those instructions are these two instructions here: save previous shadow stack pointer and restore shadow stack pointer. These are basically useful for context switching between shadow stacks. So you could imagine that you know, if maybe there's like a user level threading library that needs to maintain different shadow stacks for each user level thread, you might want to use these instructions. Also, there's this instruction called increment shadow stack pointer. So what this actually does is that this actually removes shadow stack entries without having to actually execute a ret. Now you might say, why, that seems very unsafe. Why would I want to do this? Well, as it turns out, there are certain situations when user level code needs to do sort of like non-local returns. In other words, returns that don't correspond to the series of return addresses that are on the stack. The most common example of this is language level exception handling. So, think of like in C++ or, Python, stuff like that, when you have like try catch blocks or things like that. When you implement those types of abstractions, then you have to do something called unwinding the stack. And oftentimes you're going to unwind the stack in a way that would otherwise seem unnatural, right? Because you've got this exceptional control flow. So you can use instructions like inc SSP, increment the stack pointer, to implement features like exception handling, user level exception handling, and set jump and long jump. Let's see here. So we have a couple questions here. So let's see. So is the shadow stack based in main memory? The answer is yes. It's based in virtual memory. How big is it? It's however big you configure it to be, because it's just a range of virtual memory. Let's see here. So another question, why would a ret instruction modify the content of the shadow stack in virtual memory? So the shadows, okay, so this is a question about where is the shadow stack pointer? So the shadow stack pointer, you can think of this as being like a hidden register that regular user mode code can't access directly. Instead, it's sort of manipulated by calls and rets, for example, because you see things being pushed onto or popped out of the shadow stack. Or it can be interacted with via some of these instructions I'm showing here. So like the increments shadow stack pointer, if, for example, user level code wants to implement C++ style exceptions, something like this. Let's see here. Just looking at some other questions. So I think, okay, so one question is, what if the program is meant to modify the return address by itself? In other words, like, what if you have some type of like optimized code whereby it's actually legitimate for the return address to be manipulated in a way that is different than what normal call return conventions would suggest? So that's not very common. So the most common case where you have sort of like these nonlinear call and return pairs is when you have things like language level exception handling. Sometimes you'll see this with set jump and long jump, but those are also not very common. So as it turns out, in the common case, the way that control flow should work is that you push return addresses on the stack, and then when you want to return for something, you return to the sort of the topmost return address on the stack. So in practice, you don't end up seeing a lot of problems with this. Although there are corner cases like user level threads, like exception handling, like set jump and long jump, and so on and so forth. Let's see here. And so I'll take one final question. Let's see. So why raise an exception and not consider the shadow stack as correct and return to the address contained there? Okay. So that's an interesting question, right? So the question is, well, if we're assuming that the shadow stack is sort of the source of truth, then why not just force the program to return to that address and just sort of like ignore what is currently on the regular stack? And the reason is that, well, you could do that, but if you see a difference between the shadow stack and the normal stack, that typically means that your program is foobarred in some way. So either it's been attacked, or maybe there's like a stray memory write or something like that. The return addresses on the stack have been corrupted. So you could do that. But in practice, it's kind of like, if you have a program that dereferences null unintentionally. So that'll generate a seg fault. So what you could do is you could try to register a handler for the segmentation fault exception. I remember I did this back when I was in college. I wrote a command line interpreter and I didn't know how to use strings, so it always seg fault. I just catch the seg fault exception and just continue with my day. That seemed like a fun thing to do. This, of course, is the wrong thing to do because my program was riddled with bugs. So in most cases, like with SigSev, the best thing to do is just say, this program is buggy. Let's crash it before it actually corrupts more data. So there's a similar intuition here. So yes, we could try to force the program to go back to the address on the shadow stack if there's a disagreement between the two stacks. But most likely that would just sort of paper over some sort of more fundamental problem in the program that that you wouldn't want to sort of paper over. Okay. So what's the status of this? You can use this stuff. So like if you get a recent version of GCC, you can compile with the -fcf protections flag, and this will use CET support to enable shadow stacks. There's also support for CET, or either it's supported or it's being worked on right now in both Windows and in Linux. You might wonder, why do you need support for shadow stacks in the kernel? Well, one example reason is that when the OS does context switches between different processes, the shadow stack pointer is now part of the register state that has to be saved. So, if you're writing an operating system, you have to modify the context switch code to ensure that shadow stacks are being properly saved and restored across context switches. Okay, so that's how shadow stacks work. Now we're going to look at another very common defense against control flow attacks, which is called address space layout randomization, or ASLR. So what's the basic idea here? Well, we've got our address space over here off to the right. We're looking at a 64-bit address space, looking at the user mode component of that. We've got the stack at the top, then the code, the static data, and the heap at the bottom. So as I've mentioned in some of the earlier attack descriptions, there's sort of this interesting observation that the attacker's job is much easier if the location of program state does not vary across different executions of the program or across different machines. So what are examples of some of this program state that attackers might want to know where it lives? So for example, the attacker might want to know the location of a particular overflowable buffer for some function foo in some particular call chain, right? Because if the attacker can predict where that buffer will be, and if the system being attacked doesn't use an X bits, maybe it's like an IoT device or something like that, then the attacker can overwrite the return address with the address of a buffer which has been filled with shellcode. But for that to work, the attacker has to know what that address is. So the attacker can include that address in the string that's used to overflow the stack. Now consider a libc attack, a return to libc attack. Well, in this attack, the adversary is going to try to overwrite a return address with the address of a libc function that the attacker wants to divert a control flow to. Well, once again, for this to work, the attacker has to know the address of that libc function inside the process to attack. So if the locations of program state don't change, the attacker can determine the locations of things like buffer locations or the location of libc functions. The attacker can figure out where this stuff lives just by loading the program locally and then using something like GDB to figure out where in the virtual address space this program state lives. So address space layout randomization tries to prevent this type of very simple local analysis. So with ASLR, what happens is that when the operating system loads a process, the various regions in the address space are put at random offsets. So if we look, off to the right, what we see is that now these various segments, the stack, the heap, the static data, the code, they can sort of live in different places inside the address space, which means that the attacker can no longer figure out where stuff lives just by loading a program locally, inspecting it via GDB, and then finding addresses which will be guaranteed to be valid on a different machine that's running the same program. Now, I should note that the offsets that are picked for the start locations of these regions, they're not totally random. So why is that? One example is it involves page alignment. So as I mentioned during the first half of this lecture, inside the OS, a lot of operations require page alignment. So things like mmap or mprotect, things like this, they assume that the regions of memory that are being manipulated are aligned with the page. So 4K by default on an x86 system. And so in principle, you could try to, make these different regions like the stack and the heap and the code not be page aligned, but this would make the kernel code, which does things like load process binaries, much more irritating, because now you're going to have a bunch of chunks of memory that are going to span page boundaries. And because the guts of the kernels, like, interface the block devices is page based, this would require a lot of kernel code rewriting. So in fact, in practice, these segments oftentimes have to be page aligned. That's going to remove the possibility of randomness in some of those low order address bits, because those low order address bits are going to have to be aligned on, let's say, 4K. So as a concrete example, on current 64-bit Linux OSs, you get 22 bits of stack randomness, right? So in other words, there are 22 bits of uncertainty for where the stack is going to start in a particular process. So how do you enable randomization of code and static data? Well, if you want to enable the randomization of code and static data, then you actually have to talk to your compiler and pass some specific options to make your binary be position independent. What does that mean? Well, a position independent executable basically doesn't use absolute addresses when it does things like invoke call instructions or load the value of static data variables. So instead, all of the addresses to, all of the references to code and static data, they all have to be indirect somehow. So for example, like rip relative to the current PC, or maybe via table lookup, indirect via register. And so if you compile your code with a flag like PIE, that makes it safe for the code and the data regions to kind of be moved around. And so how is this actually implemented inside of a kernel? So let's take a look at how Linux does this. So if you look in the kernel source file, mm/util.c, then you'll see that there is a function conveniently named randomize stack top. So what's going to happen here? Well, we're going to declare a random variable. We're going to check to see basically if the kernel should actually randomize the start location of this process's stack. So just for context, this code here is being called when we're initially setting up the address space for a new process. So we check some flags and say, hey, should we be randomizing stuff? Should we be implementing ASLR? If the answer is yes, then we make a call to a random number generator. We basically AND off some bits there. So this gives us, in practice, 11 bits of randomness on a 32-bit Linux host, 22 bits of randomness for a 64-bit host. We then shift that variable to the left by the page amount. Remember, things need to be page aligned. And then we take the stack top that was passed in here, and then we move it around based on the value of the random variable. So that's literally how we randomize the starting place for the stack. Note here, there is some unbearably inconsistent brace indentation here. It makes me sad every time I look at this slide. We're somehow not putting this thing at the end of this line, but then this thing is on the same line. This is just, I weep for the future if this is what they're teaching people in school. Anyways, moving on. If we look in fs benfunct_elf, so once again, this is a function that is called by the kernel when it's creating a process and initializing the address space. We see something similar here with randomizing the break. The break is the starting point for the heap. Right, so here we're just saying, should we be randomizing the starting place for the heap? If so, the start of the heap is going to be essentially, some randomized offset generated there. So ASLR is basically a common defense now. You'll see this in Linux, and you'll see this in Windows as well. Somebody has said in the chat window that what I just called out was the standard brace position according to Linux kernel coding style guidelines. Yeah, I'm debating whether that's a good idea or not. I know that now I'm going to get all this angry hate mail from Linus, so clearly it was a mistake for me to accept this guest lecture position, but I don't have a time machine, so I look forward to getting all the spam from the Linux aficionados. Okay, so moving on. Now we're going to talk about another defense against some of the attacks that I just mentioned. And it's a pretty straightforward one, and it involves randomizing the layout of structs. So let's take a look inside of Linux's VFS structure. So VFS, that's the virtual file system. Roughly speaking, this allows you to implement sort of like abstractions for file systems inside of a kernel. So there are many different file systems out there, ext4, btrfs, things like that. But they all implement, to a first approximation, the same set of operations. So, open a file, read a file, so on and so forth. And so the file operation struct here, what this does is act as a level of indirection. So a concrete file system like ext4, for example, defines concrete implementations for all of these functions here. And then when a process issues, an open call or a read call, the OS can sort of use this higher level abstraction of a file operation to figure out which specific file system implementation method to call. So if you look at all this kind of stuff, you might say, well, look at all the function pointers, right? Function pointers are their code addresses, they're code pointers. So this looks very tempting for you as an attacker. You might try to find the location of such a thing inside the kernel code. And if you can trigger a buffer overflow, some other type of corruption, you might want to then try to hijack control by overwriting one of these things. So if we look down at the bottom, though, we see this randomized layout incantation. So what does that do? So the randomized layout incantation instructs GCC to generate different field offsets for things like the open pointer, the read pointer, so on and so forth. So each time you compile the code, you'll get different layouts for this particular struct. And so why is this helpful? Well, the reason why this is helpful is because it makes it harder for evil code to read and write known values at known offsets, right? Because every time someone compiles the Linux kernel, this particular struct will have a different order for all of these function pointers. So, in general, adding non-determinism to the environment under attack makes it more difficult for the attacker to actually successfully exploit that environment. So stepping back a bit, what have we been thinking about in this lecture? Well, at a high level, what we've been thinking about implicitly is this notion of a control flow graph. So for example, if we look at the control flow between C statements, we might see something like this for a simple program. So the specifics are not very interesting here. But what I've done is I've labeled sort of each of these C-level source code statements with a line number. And then off to the right, we see the control flow graph for this program. So for example, if we look at nodes 0 and 1 corresponding to source code lines 0 and 1, we see there's just one arrow coming there. And that means that in a legitimate control flow, source code line 1 should always follow from source code line 0. Now, if we look at source code line 1, it actually has two arrows that are coming from it because this is sort of the top of a while loop. So that while loop can either sort of terminate going all the way to the bottom here, or it can go to the first statement in the body of a control loop. So that's the basic idea of a control flow graph at the C statement level. And you could imagine that you could create a similar type of control flow graph at the assembly level. So for example, at the basic block level. And that is precisely what control flow graph integrity tries to do. But there's this question of who gives us the control flow graph? Who generates that delightful picture that I showed you on the last slide? So one way you could try to think about generating the control flow graph is that it comes from the compiler. So the compiler generates the CFG, the control flow graph, during program analysis. And then the compiler is going to inject instrumentation at all these sites in the program that do indirect jumps. And that instrumentation will consult the CFG graph somehow, and then check whether a particular jump target, whether a particular destination for a jump is actually valid. You can also try to imagine doing all this CFG stuff dynamically. So trying to infer the control flow graph using a mechanism like the shadow stack. So that's exactly what we just discussed before. Now it's possible to implement shadow stacks at the software level. You could have the compiler instrument each call to push the valid return address onto a software maintained shadow stack, and then have the compiler inject instrumentation for rets as well to pop that software maintained shadow stack. We just discussed Intel CET, which does this in hardware. So the shadow stack resides in isolated memory that's inaccessible to application code, and the CPU will automatically do the manipulation for the shadow stack during the calls and the rets. And so that's the approach that Intel CET takes. But at a higher level, there's this question of how accurate is the control flow graph? And this accuracy is always a big problem. Like if you do a search for Obama paintings, be prepared to find just hilarious stuff. Some of them are like moderately ridiculous, but somewhat accurate. This is one of my favorite ones here. This is a real thing that I searched for on the internet. This image is now in my browser cache. This is apparently a naked Obama riding some type of freedom unicorn. What I love about this is the attention to detail. If you zoom in there, you'll see that he's wearing an amulet of power. I have no idea why that amulet of power is there, but somehow this makes me think that everything's going to be okay. I digress, of course. We were talking about control flow graphs. So if you have inaccuracies, you can have problems with enforcing control flow integrity. So for example, if you have an under-constrained control flow graph, this may cause false negatives. By this, I mean that control flow attacks may actually go undetected because your graph is under-constrained. So let's assume that the legitimate CFG looks something like this, right? So let's assume that like once again, those 0 or the 1 or the 2, those are basic blocks, those are C-level statements, something like that. So if the legitimate CFG looks like this, you might have an under-constrained CFG that looks something like the following. So we have everything we had off to the left, but then some extra nodes over here, right? So it's under constrained because it doesn't actually prevent all of the bad control flows. Like in this example, the control flow from 0 to 4 should not actually be allowed. But in this under constrained CFG, it is actually allowed. Now you can also have an over-constrained graph. That's going to cause false positives. So with an over-constrained graph, a valid control flow may actually be flagged as illegal. So once again, suppose the legitimate CFG looked like this, the over-constrained CFG might look like that, what we see on the right. And so in this case, a legal transition from 2 to 3 would be disallowed because there isn't an edge for that in the over-constrained control flow graph. Okay, so the take-home point of this is that it's very important to have an accurate control flow graph. And sort of whenever you see something like this, when you talk about false positives, false negatives, as a security person, one thing you should always be aware of is that sort of false positives are really, really bad for adoption of your security tool. So if you see a tool that's constantly telling you the sky is falling and it's wrong some non-trivial portion of the time, people just turn your tool off. And so as a preview of coming attractions, that means that typically people are much more comfortable with false negatives in control flow integrity because they're saying, well, I may miss something, but I'm not going to constantly be alienating my user base by constantly giving them false alarms. Okay, so let's see here. So now let's look at a concrete example to illustrate the challenges of precise CFI. So let's imagine that we had some C functions over here. One of these functions is called less than sort. It takes an array and a length that's going to sort it using a less than comparison. GT sorts, greater than sort, has the same sort of function signature as less than sort, but internally it's going to make a call to the sort function and it's going to invoke the the greater than function. And so if we look at the rest of the code, it kind of looks as you might expect. So we have this sort function here, which takes an array, its length, and then some type of comparison function. And then inside of the sort function, we call the comparison thing, and then figure out how we're going to sort two elements, AI and AI plus 1. And then up here we just have the concrete implementations of less than or greater than. Okay, so let's think about this fairly simple code in terms of how we might come up with a CFI graph for this. And so this is a sort of exercise that you see in a lot of the CFI papers. They'll use this example. So imagine that you wanted to have a compiler enforced static CFI. So what the compiler might try to do is find every instruction that can be a legitimate target of an indirect branch. And then during compilation, it's going to assign each of those instructions a unique ID. The compiler is also going to associate every indirect branch instruction with a set of valid target IDs. In other words, a set of valid target instructions to which that indirect branch can go. The compiler will then instrument every indirect branch to determine whether the current jump target is a valid one. So in other words, the compiler will inject new instructions that the developer didn't put there that are going to essentially consult, it's going to introspect the jump target and say, hey, does this jump target fall in the valid set of target IDs? So if you look at the control flow graph for this C code on the left, you might see something like what you have on the right. So these heavy arrows here are indirect control flows, and then the light arrows are direct control flows. So for example, we see the call sort here. That's a light arrow because we know with complete certainty that we're going to be calling where? Well, to the sort function. In contrast, if you look inside the sort function itself, here we see an indirect control flow, right? When we do a call and then this comp function, well, depending on what function was passed in as an argument, as we see here on the left, we're going to jump to one of two possible targets, either less than or greater than. And so we see some other relationships here as well. So for example, like this ret instruction in less than, well, that ret should go back to some target ID, in this case 2. So that corresponds to the instruction in sort that is right after the call to less than. So what are some examples of potential compiler inserted CFI checks that might be generated? So for example, if we look at the less than ret, this is what I was just describing. So this ret instruction here should only return to the instruction at ID 2, the instruction right after the call indirect through the function argument to sort. If we look at the call to the comp thing here, this is also what I was just talking about. So this call can go to one of two places. It can either go to less than or greater than. Now, the decision about which one of these choices is correct is actually dependent on the history of the control flow. So if we look at this call instruction here, it's only valid to have this call go to ID 3 if the code got to the sort function by coming through less than sort, right? In other words, it would be inappropriate for this call instruction in sort to go to ID 3 if sort had been invoked via a call to greater than sort. So in other words, this analyzing the correct control flow for this call instruction in sort is actually dependent on some prior history. Now there's a challenge here, which is that tracking cross-jump control flows is actually expensive, right? You can imagine that compiler injected instrumentation might need to access a data structure several times for each jump. In other words, you can imagine that the compiler injected instrumentation is actually using some type of call stack, for example, to actually determine like, okay, well, I'm trying to determine where this call instruction should go to. How did I get to this call instruction? I check some stack and I say, oh, okay, I came through a call to less than sort. So that means that the only valid target for this particular call in this particular execution history is to go to ID 3, to go to less than. Now, the problem here is that jumps are very common. So if we were going to do the naive thing of like checking a full-blown data structure for every control flow and maintaining that data structure whenever we sort of transfer the value of RIP to some different value, that would be very expensive. And so let's see here. So what does this mean with respect to how CFI gets implemented in practice? So as it turns out, real compiler-based CFI oftentimes relaxes constraints. In other words, it oftentimes allows control flows, which strictly speaking are not allowed by the exact control flow graph. So for example, many compiler-based CFI schemes allow a ret to return to any call preceded instruction. So what do I mean by that? So if we look at less than sort, so there's a call instruction right here, I'm showing with my mouse, and then at ID 0, we see some instruction. The instruction at ID 0 is a call preceded instruction. Now, if we relax the control flow graph that we're trying to enforce, then what we might say is that we might say, okay, I'm the compiler, I'm only going to inject instrumentation to determine if a ret returns to a call preceded instruction. So what that means, for example, is that if we look at less than over here to the right, a relaxed CFI scheme would allow this ret to return to not only ID2, which is the right place, but it would also allow ret to return to the instruction ID 0, because the instruction ID 0 is a call preceded instruction. So that's an example of the type of relaxation that you could see to avoid having to do some of these heavyweight data structure manipulations to keep track of a precise history of what functions were being executed. Another common relaxation is that a jump can go to any function start or any allowable basic block, where an allowable basic block might be the start of a C level control statement, like an if, an else, a while, and etc., and something like that. So once again, that is a relaxation of the constraints. But what it means is that the checking that the compiler injected instrumentation has to do is it's much less performance intensive than if it had to check a precise history of all execution stuff. Because for example, if you wanted to determine if an instruction is call preceded, then all you have to do is just look backwards a few bytes, starting at the address of the jump target. So, you know, if we want to determine if, let's say, ID 0 in less than sort is call preceded, just literally look backwards a few bytes in the code segment and see, is there a call instruction there? So in practice, we have these relaxed constraints because we care about the performance of things. But this does allow for invalid control flows. And there's this natural question of, well, does this mean that relaxed CFI is actually useful? You know, why do people use relaxed CFI? Well, because it has no false positives. And as I mentioned, whenever you're thinking about designing a security tool, you always have to be thinking about false positives, because even very small false positive rates will make users very unlikely to use your system. So relaxed CFI, because it's relaxed, has no false positives. It does have some false negatives, as I was just discussing. Now, I want to emphasize the point that relaxed CFI is still better than nothing. So for example, if we look at this call inside of sort, well, this call here can't jump to the middle of any function. If let's say the relaxed CFI constraints are that we only allow calls to go to the beginning of a particular function. So this is nice. So the sort call can't go to an arbitrary place, right? It can go to some places that are not allowed by the strict CFI graph, but perhaps this is the price we pay for performance. And so because most people don't want these false positives and they don't want to, because people don't want false positives and they don't want to pay the performance penalty for tracking at runtime a precise control flow history, most of the proposed CFI systems that you'll see use relaxed CFI. Okay, so that is the end. I'll actually go to the previous slide. What's happened? Oh God, I think I cannot share the screen. Let's see, 1 second. Share screen. Okay, so screen sharing has been disabled for some reason on the host now. Maybe I can do it. Sorry, okay. We will be back with the slides in a second. Here we go. Okay, sorry about that. So that is the end of my prepared material. And so now I'd love to take some questions. I see there's some questions in the Q&A window. So let me address some of those. So one question is, what is my opinion of Intel processor trace? So I generally think that it can be very helpful. We'll talk about this a little bit tomorrow. I should say that I think that a lot of the sort of performance counters or other types of like hardware-based security mechanisms that people like, you know, Intel and AMD and ARM are doing, I do think that they're actually a good idea. And I do think that they've actually improved the level of security that real systems have. Now, as we'll see in particular with SGX, it's still difficult to get these details right. And so my overall opinion about computer security is that the bar is being raised and it is becoming more difficult for attackers to subvert systems. But we all still know that attacks still happen. And I think what's ended up happening is that even though the level of sophistication needed to defeat things like ASLR is getting harder, because we have things like the internet, you know, if one person can do something, that means that everyone can do it. All the script kiddies can do it. And so we'll see in tomorrow's lecture how the level of difficulty has gotten harder, but it's still possible to defeat some of these things. Let's see, someone asked, let's see, so Fabian asked, do people use canaries to protect function pointers as well? The answer is typically no in practice. Now, there's nothing that prevents you from doing this if you so choose, right? Because the same mechanism applies, right? So if you want to use a canary to protect some piece of data, then basically you just put the canary between that data to protect and something that you consider to be overflowable. So it's definitely possible, but because of, once again, performance, people typically do not put canaries in front of everything that a canary could be put in front of. So typically people just use canaries for the stack. Now, we're not going to talk about this tomorrow, but if you look at the Linux kernel, there's also a bunch of different sort of protections they put in there to protect the kernel in various ways. So like there's a configuration option you can use with the kernel to basically try to put guard pages next to various sensitive kernel structures. These are basically pages that are unmapped, right? And so if a buffer overflow or some type of like memory vulnerability tries to touch one of these pages, then what's going to happen? Well, it's an unmapped page. It's going to generate a page fault, and page faults to a first approximation are always fatal in the kernel. And so once again, typically when you determine that there's been a control flow breakage, you just want to terminate the program, because trying to continue executing the program, who knows what state is corrupted, who knows whether you'd go on to, you know, damage more data that's written to the file system or sent over the network. So in the kernel and in some security conscious applications, yes, you do place canaries in other places besides the stack. That is not a common thing. Let's see here. Okay, so from Muhammad, I have a question here. Could you please elaborate on why false positives are way too important for a security analysis tool than false negatives? Right, so this is a great question. So the thing is, it's just because of human nature. You know, there's not some like deep sort of theoretical reason why false positives are much worse than false negatives, right? And it is true that in some, like, let's say mission critical situations, you're building a spaceship, or I don't know, you've got running a nuclear power plant, you can't have false negatives, right? But I think what ends up happening is that most people's practical sort of understanding of sort of risk is that they view absences of attacks as the common case, right? So a user just thinks that by default, attacks are not happening. And so false positives as a result get very irritating because your default position is that, well, by default, attacks shouldn't be happening. So I keep getting these like, text messages or emails, this tool's complaining, I'm just gonna turn it off. Now you might say, aha, but it could be that like the downside from an attack is so devastating that you should put up with those false positives. But I mean, what we see empirically is that people don't think this way. People sort of don't have that type of risk analysis. And so because people tend to underestimate the damages from a successful attack, and because people basically get easily irritated by false positives, in practice, when you're thinking about deploying a security tool, it's very important to reduce those false positives just to get people to use stuff. Okay, so I have a question from G1 here. So that question is, how much performance overhead would be considered negligible for security? That's a great question. This is kind of in the eye of the beholder because, once again, in some situations, if it's a quote unquote high security situation, you're willing to pay 2x, 3x overheads. But for a lot of people, in a lot of situations, if you're paying more than, let's say, 5 to 10% overhead, that's oftentimes a non-starter. That's a bit unfortunate because like a lot of the workloads that people run are not actually all that performance sensitive. But you can imagine, for example, things that are user facing, if a 5 to 10% overhead would, for example, cause frame rates to drop, that's noticeable. If it would cause a GUI to become less responsive, that's noticeable. For some types of web services, a 5 to 10% overhead, if you're running at scale, that could end up being, in terms of, let's say, energy costs, that could be tens or hundreds of millions of dollars of electricity. So there's constantly this sort of trade-off in the mind of a security engineer in terms of what are the risks that are actually reasonable for me to worry about? What are the sort of consequences of being successfully attacked via one of those risk vectors? And what type of performance or availability penalty am I willing to pay to stop some of those attacks? Okay, and let's see, another question from Bruno. So how viable do you consider side channel attacks? So we're gonna talk about some side channel attacks tomorrow. So your specific question though is how viable do I think side channel attacks involving power or temperature, how viable are those in comparison to attacks that look at things like memory corruption, like what we've just looked at today? So it's a funny question because let's say 3 years ago, if someone had asked me the question, do you think that side channels are like an interesting thing to think about? I say yes. But if someone said, do you think that side channels are a practically worrisome thing to think about? I would have said probably not. Because a lot of the side channels that people have been talking about in the academic literature, they're very contrived. So in particular, attacks that were on things like temperature. So like there's some pretty funny attacks that you can do if you have two computers, one of which is controlled by an attacker, the other one of which is not. Both of them have temperature sensors, let's say, on maybe like the GPUs or the CPUs to prevent overheating. And so let's say that the attacker totally controls one machine and then somehow manages to launch a remote attack on the second machine and now wants to exfiltrate data out. Some secret file, for example, that's stored on the second machine. But let's say that this second machine, maybe it's air gapped or, for some reason it can't talk directly to the first machine. So what the attacker can do is actually try to heat up the second machine by running computationally intensive workloads. And if that happens, and if the attacker controls the temperature sensors on the first machine, then the attacker can look and see when the temperature rises. And so, for example, when the second machine wants to exfiltrate a 1, it runs hot and then allows the first machine to detect the rise in temperature. When the second machine wants to send a 0, it runs cold. It basically doesn't run a lot of stuff, and then so on and so forth. So like this side channel mechanism has a bit rate of something like, 2 bits an hour, which is very, very low. And so although it's like super hilarious and like it's very interesting to know that things like this exist, 3 years ago, if you would have said to me like, hey, should someone be practically worried about those kind of attacks? I say no, unless you're in a very, very sort of highly sensitive situation. You're, running NSA workloads or some very sensitive corporate workloads, so on and so forth. But as we'll discuss tomorrow, side channels involving the caching layer, L1, L2, side channels involving microarchitectural sharing, and we'll talk about all this tomorrow. Those attacks have been shown in the past, 3 years via Meltdown, Spectre, Foreshadow, all those kind of things. Those are real attacks that people have to care about. So I consider those types of side channel attacks quite relevant these days, particularly for the architectural community. Some of my own research involves how to remove some of those side channels. So I say those types of side channel attacks are very important. With respect to other side channel attacks involving power or temperature, I think they're important in a sort of small set of situations, but they're not sort of attacks people should be worried about sort of in the common case. Let's see here. So I have another question. Does CFI imply a check at runtime to see if a jump address matches any possible function starter basic blocks? It does. At a high level, it does. Now, the details are specific to how the actual concrete CFI scheme works. But for example, if we think about the Intel shadow stack approach that's enabled via CET, that is a form of CFI. That is a form of control flow integrity. And so what happens is exactly what has happened, or what is mentioned in your question. So at runtime, there is a check. So at runtime, there is a check to see if the return address in the shadow stack is the same return address as the one on the normal stack. Similarly, for some of these compiler-based CFI schemes that I was mentioning, yes, there will be a check at runtime to basically determine whether a particular jump is going to a quote-unquote good place, where good is defined with respect to the specifics of the CFI scheme. So for example, if there's a ret, the CFI scheme might want to make sure that the ret target is a call preceded instruction. And so like the naive way to do this is to literally have the instrumentation read the bytes in the code segment immediately before the desired jump target. Return target, right? So literally, you've got a return instruction somewhere. Actually, we can see this on this slide here. So, let's say we're looking at this less than function. We're looking at the ret here. So let's say we had a CFI scheme that's only going to allow that ret to go to a call preceded instruction. So we see that the ID2 here, this instruction, that is a call preceded instruction. We also see that ID0, this instruction, that is also call preceded. So how might the compiler go about checking or injecting instrumentation to check this? Well, the naive way is to actually, in the instrumentation, is to look at the address that the ret is trying to return to, and then literally have the instrumentation look at the immediately preceding bytes in the code segment and say, can those immediately preceding bytes be interpreted as a call instruction? And if the answer is yes, then the instrumentation allows the return to proceed. If the answer is no, then the instrumentation causes the program to fail. So yes, there will be some runtime check there, but once again, it depends on the exact specifics of how things work. So for example, if you're interested in the details of this, go check out Clang. I think the Clang team, they wrote a paper about how they implement CFI, and they go into great detail about all sort of the tricks they do to make the CFI efficient. Let's see here. So someone asked, can you please upload the slides? Yeah, they will be uploaded later, but soonish. So those should be somewhere that you can access them in the near future. With respect to will a recording of the lecture be available afterwards? That I'm not actually sure. So you should ask some of the people who are organizing the summer school. I don't actually know that. And then let's see here. There's a question about, I assume that we've been talking about human attackers in this lecture. And that's right, we've been talking about human attackers. And so the question is, will neural networks or AI one day be trained to be an attacker? The answer is yes, for sure. I mean, kids today with their machine learning stuff. So I've already seen a couple of startups that are trying to use AI to, automatically figure out various ways to break into systems. I don't think this stuff is ready for prime time just yet. But of course, because people want to use AI to do everything, of course, this will eventually be done. I mean, I will say that like one reason why, not necessarily AI, but sort of automated attempts to generate exploits, I think those attempts will become more common in the future because it is actually getting more difficult to exploit machines. This is something I kind of alluded to earlier in the lecture, but even though there are still constantly attacks coming out, it is becoming more difficult to find the associated vulnerabilities. And so when we look at some of these more complicated attacks that people use to break into Chrome or things like that, they're multi-step, they're pretty sophisticated. They typically leverage a series of vulnerabilities to sort of string together, separate pieces that the attacker then combines to launch the attack. So I can imagine that, attackers will eventually start putting more effort into tools for automatically generating or at least helping to assist with attacks. And some of these tools already exist. So tomorrow we're going to talk about ROP attacks. And so as a preview of the coming attraction, there are already tools that attackers can take off the shelf to try to find the components in ROP attacks. This sounds very abstract now because we haven't talked about the details of how they work, but rest assured we'll talk about that tomorrow. So, is AI-based sort of automation sort of the future of attacks? I'm not sure that AI in particular is going to be that helpful, but I definitely think that sort of automation in general is going to be very important for attacks of the future because these defenses are getting better and better. All right, any last questions before we sign off for today? Okay, I'll give people 10 more seconds in case they want to type out any questions, or maybe just the outrageous clarity of my lecturing was just so forceful that there are no more questions. All right, it looks like there are no more questions. So great. So thank you so much for showing up, and I will see you tomorrow where we will talk about some more advanced attacks and defenses. Thank you.